Hello everyone, my name is Ekaterina Lobacheva, and today I'll present you a paper on power loss in deep ensembles. This is a joint work with Nadezhda Chirkova, Maxim Kadryan, and Dmitry Vetrov from Bayesian Methods Research Group. When you want to use a neural network model to solve your task, it is important to understand how the solution quality depends on the shape and size of the model. In our work, we are focused on the most standard type of ensembles of neural networks, so-called deep ensembles. Usually in deep ensembles, several member networks of the same shape and size are trained from different random initializations. And then their predictions are averaged to obtain the prediction of the ensemble. We investigate how the ensemble quality depends on the number of networks, or so-called ensemble size, and the size of the networks. We vary the size of the networks by changing their width. Generally, we look at the behavior of the ensemble quality in three directions. When the size of the networks is fixed, and we increase the number of networks. When the number of networks is fixed, and we increase the size of the networks. And when we increase the total number of parameters in the ensemble, while using the optimal ratio between network size and the number of networks. In the experimental part of the paper, we work with the classification of CFAR images using VGG and wide-ResNet networks. The results for all dataset architecture pairs are similar. Therefore, in the presentation, we show only the results for VGG on CFAR 100. As quality metrics, we consider negative log likelihood and calibrated negative log likelihood, because they are widely used for model assessment, especially in uncertainty estimation. Negative log likelihood, or NLL, of a model on a dataset D is the negative sum of the log probabilities for the correct classes predicted by the model. For theoretical correctness and empirical stability, we work with the model average version of the metric. So we take an expectation with respect to all possible models. In our case, with respect to all possible ensembles of size m. In practice, using NLL for model comparison may lead to an arbitrary ranking of the models. For the correct comparison, models need to be calibrated by choosing the optimal temperature of the softmax. In case of deep ensembles, the temperature can be incorporated in the softmax in two different ways, namely before and after averaging. The standard way is to apply temperature after averaging, because in this case we plug the ensemble into the calibration procedure commonly used for an arbitrary model. We apply temperature before averaging, because such procedure behaves more stable in some non-standard cases. At the same time, in all practically important cases, the results of these two calibration procedures are almost the same. In our work, we discover that in most of the cases, NLL and CNLL of an ensemble behave as power laws. A power law is a function, which formula you can see on the slide. So it converges to an asymptote and behaves as a linear function in log-log scale after the subtraction of the asymptote value. First, we look at the behavior of the ensemble quality when we increase the number of networks. We prove theoretically that asymptotically both NLL and the close approximation of CNLL as functions of ensemble size behave as power laws. To show it, we firstly formally prove that the NLL of an ensemble behaves as power law as the number of networks n approaches infinity. The same result holds for NLL with any fixed temperature in the softmax. Then we prove that the lower envelope of asymptotic power laws is an asymptotic power law. Therefore, the lower envelope of NLLs with different temperatures asymptotically behaves as a power law. Finally, CNLL and the lower envelope of NLLs only differ in the order of expectation and minimum operations. And in practice, their values are very close. As a result, approximately, CNLL also asymptotically behaves as a power law. Infinite ensembles are possible only in theory. In practice, the ensembles of finite range sizes are used. Interestingly, in our experiments, we find that NLL and CNLL behave as power laws not only asymptotically, but also for all finite range ensemble sizes that we considered in the experiments. Let's now look at the behavior of the ensemble quality when we increase the size of the networks. For a single network, CNLL behaves as power law, while NLL experiences a double descent behavior. For the ensemble of more than one networks, NLL still experiences the double descent behavior, while CNLL starts increasing at some network size. As a result, both of them cannot be approximated with power laws. The increase of ensemble CNLL may be a consequence of under-regularization or the decreased diversity of large networks and needs further investigation. Finally, we investigate the behavior of the quality of the ensemble when we increase the total number of parameters in it. The dashed diagonal in the right plot corresponds to the fixed number of parameters in the ensemble, or memory budget as we call it. We choose the minimum CNLL value at each diagonal and plot the resulting value in the left plot. As a result, we observe that CNLL of the ensemble also behaves as a power law, as a function of the total number of parameters. In the previous slide, we chose the optimal ratio between network size and ensemble size for each memory budget. The interesting finding here is that for a fixed memory budget, the optimal choice in most cases is not to take one large network, but to split the budget and train an ensemble of several smaller networks. We call this ensemble a memory split. It is true even for quite small budgets. For example, if our budget matches the size of a standard VGG, then we should split it and train an ensemble of 4 networks in order to obtain the optimal quality on CFR100. We observed this effect not only for CNLL, but for accuracy too. One may wonder whether memory budget splitting slows down training or testing in practice. In our experiments, we observe that an ensemble of several medium-sized networks is only moderately slower than a single wide network. The discovered power laws not only closely approximate ensemble quality, but also allow predictions. In our experiments, we show that it is possible to estimate power law parameters using the values of CNLL for small ensembles, and then accurately predict the quality of large ensembles without training them. For example, for VGG on CFR100, we obtain the error of 1–2 orders smaller than the values being predicted. It is also possible to predict optimal memory splits for different memory budgets. To do so, we choose the point with the minimum value at each diagonal of the CNLL plot, where the values for large ensembles are predicted with power laws. Again, on the slide you can see the example for VGG on CFR100. In most cases, the discovered power laws predict either the exact or the neighboring memory split. If the neighboring split is predicted, the difference in CNLL between the true and the predicted splits is negligible. To sum up, in this paper we analyzed the behavior of the quality of neural network ensembles and found that it can be closely approximated with power laws in a lot of cases. The discovered power laws can be used to accurately predict the quality of large models and optimal memory splits for fixed memory budgets. The paper and code can be found as the links on the slide. Thank you for your attention.